So, a hearty welcome to all the participants in this webinar, the distinguished speaker, our Professor Baradakanta Mishra. We have Vice Chancellor of SOA University, Professor Ashok Mahapatra, and the Director of IMMT, Bhubaneswar, Professor Sudasatta Basu, and our every time attendee, Dr. A. Sanant Kumar. He has
I think we should give maximum, the person who is attending maximum lecture should get an award to encourage people to hear this.
No, that
age doesn't matter, position doesn't matter. It is the dedication to education.
We'll definitely have that award. No issue. So today is the actually 12th distinguished lecture that is being jointly organized by our INA Bhubaneswar chapter, SOA University, and IMMT Bhubaneswar. So in this, every month actually we are trying to have at least 2 such lectures, and this month, fortunately, we will have 3. One is actually today on 13th, one of the top persons in 5G networks standard setting person worldwide will be really speaking, and on 23rd, this Professor Gopal Jagdish from IISc Bangalore will be speaking. So we are really fortunate to have all these things. Now, today, being the Return Car Festival in Puri, a lot of crowd is there. So many people may be really watching that car festival. So our attendance may be less, but let us hope that in future it will be more. And Lord Jagannath's blessing will be there with all of us to take it forward. Now, with this, I would first like to request our Professor Ashok Mahapatra.
I think, sir, let Dr. Basu speak. Let him say that somewhere. My request to you, sir, this time let Dr. Basu talk about it.
No.
Then
No, Professor Basu will say
he will have thinking always Dr. Mahapatra speaks.
No, he will have 2 other jobs to do. He will definitely talk about IMMT. He has to also say, introduce our, speaker, Dr. Baradakanta Mishra, who has been the former director of IMT for 12 years.
Yes.
So naturally,
okay,
that thing actually should be with him. Okay.
Okay, and, thank you, sir. I think we'll, okay.
Let us be brief and give a bit of time to Professor Mishra.
Shall I start?
Please.
Okay. I think good afternoon. Jai Jagannath. My greeting on the occasion of Bahuda Jatra. It is the Jatra of return journey of Lord Jagannath from his Ratna Janmabhumi or Adab Mandapa. I wrote an article today. Bahuda Jatra, we all have to return journey. We have forward journey, and life is a journey had to return to the heavenly abode called Bahuda Jatra. So every Rath has a return. I always say we are human being is a car, body is a car, the soul is a Rath. Bhagavan Jagannath, our Jatra is back and forth to Lord and back to the earth. This is Rath Yatra. Rath means body. So after having said that, few words about university. We all know that everybody know about university, but the good thing is that this year NAC accreditation, we could get 3.88 out of 4. This is the third cycle of the 3 cycles accreditation, 2009, 2015 and 2022. Unfortunately, because of COVID, this accreditation of 2020 was further delayed by 2 years. So this year we had 4th, 5th, 6th May for the evaluation, and we have a panel of 5 people those who came for evaluation. So that is regarding day for yesterday. We had Times and India scoring. Our medical science got 16 number in the rank out of 490 those who entered the ranking system by the Times group. I think India Today groups. So I think that way university has made an impact in Odisha, in India, and over the world at large. The question is that what has been our vision? Our vision was to have quality education. What is the new education policy? Is a quality, not quantity. Skill and innovation. Of course, we have 36 research laboratories. We have large number of postgraduate students, those who do research. We take 150 post PhDs, and after the 100 are the financed by the university, and 40 are the self-financing people. So every year we are producing almost about 130 to 140 PhD. We make them to write 2 quality paper in Scopus Index Journal. That's how, even during pandemic, our publication rate was last 2 years around 2000 every year, each year. So when we stopped the offline classes, so our letter had gone to faculty during this close down, shutdown, lockdown, whatever adjective used, they should produce at least 2 to 3 papers per the year. They cannot give the excuses that they're taking too much of classes, are exhausted sitting at home. So I think our faculty positively responded to our calls and also did the justice to university by publishing huge number of quality papers. We have a research lab on biofuel, nanotechnology. Of course, we were part of the vaccine trial, the 12, one of the center of the 12. I must tell you that in wave 1, we had 2,400 beds of COVID, and wave 2, we have 2,750 beds COVID. Now we have got 500 COVID beds hospital activated. In last 15 days, we have admitted 50 COVID patients. So COVID is coming back. Yesterday, out of 554 cases in Odisha, 250 were from Bhubaneswar, and always 100%. If you take 100 cases, 50% are from Khordha. So we have to be very careful. And in last 1 month, I have twice COVID tested, because twice I have been come in contact with COVID patient. Yesterday, 2 days back before going to Banaras, I got COVID test. So 3 times COVID tested in last 6 weeks or so. I think we have a lot of things to do so far the science and technology is concerned, so far the NEP is concerned. Even though you think that we have done well in NAC grading, that is not the things to feel happy. We all know what we are, what to stand, what should our roadmap for 5 years. Currently, when the NAC completed their evaluation, they say we lack more digital technology. That was one of the comments they made. We must apply more digital technology our day-to-day affairs. 1, 2, we should have more international students. I thought these are very appropriate and healthy comments. We must take the comments of our peers, our evaluator, and well-wisher. I think we all look forward to Professor Mishra's lecture, because my talking has no meaning. I think most of them know very well our university. Our aim is to not get complacent, but go ahead. That is what I say. Man may come and man may go. I will go forever. The Vice Chancellor will come. Dr. Acharya has started a very, very important lecture. In last 2 years, we have done a started SOFR lecture soya less. So fortnightly soya university, fortnightly lecture, weekly lecture at departmental level. We have a wellness center. We have started large number of postgraduate super specialty courses like cardiac surgery, neurosurgery, or many 12 super specialty courses started. Bone marrow transplant, liver transplant, kidney transplant started. So we are making a socially concerned factors operating in our day-to-day life. So I think I must stop here and hear our speaker, because otherwise all the time will be taken by me only. Thank you very much.
No.
Thank you, sir.
Thank you very much, Professor Mahapatra. And one thing just I would like to inform that Professor Mahapatra actually told about Bahuda today, and like Lord Jagannath, Balabhadra, Subhadra, they are coming back to this thing from Janmavedi to Karmavedi. Today, I'm very sorry to say we lost one of the great person, at least in engineering person, and even teacher of our Professor Misra. And though I have not really been his direct student, but definitely he was my principal. And he is no other person than Professor Somnath Misra. So a great soul. And he also happens to be from Puri and student of IISc. Okay. Now, let us all pray for the Mukhya of Professor Misra. And with this, let me request Professor Sudasatta Basu to first tell something about the IIMMT. Last few times, actually, we missed him because he was busy in other things. And what is more important is he should be the right person to introduce his predecessor, Professor Misra. Professor Basu, please.
Thank you, Professor Acharya, for giving me this opportunity to talk about our institute, CSIR Institute of Minerals and Materials Technology, Bhubaneswar. We are going to celebrate Diamond Jubilee, our 60th year of existence next year. That tells that how old this institute and how long it has been coming to nation's requirement of mineral processing, extractive metallurgy, materials development, then environmental impact or the environmental and sustainability that is very well tied to mineral sectors or mineral processing, mining and metallurgy sector. Over and above, we also work in modeling, as Professor BK Mishra will talk about today. He has done a tremendous work here at IIMT while he stayed about 11 years as a director of this institute after coming from IIT Kanpur. We currently focus on some of the critical minerals. The current requirement is lithium. So one of the critical mineral that we are working on is on lithium. Lithium sources are very less, almost not there in India. We are working on whatever sources we have in mica mine in Jharkhand or in some places in Karnataka. But we are also working some of the lithium sources available in Myanmar and of course in Central America. So Australia, but Central America mines the sample we get from Tata Steel. Who are Tata Chemicals, I would say, not Tata Steel, Tata Chemicals, who are into the business of e-mobility, the Tata Group, the Tata Motors, and along with that is working is Tata Chemicals to resource lithium cobalt. So we were working on this. We were working on a lot of rare earth, neodymium oxide to pure neodymium 49, which is not made in our countries for NDFEB magnets. These are the new initiatives that we have taken in the recent past. We're working lots on material. So there is an advanced material mission runs currently at IMMT, which is handled by me on advanced materials, mostly showcasing new materials, functional material, and the devices like optoelectronics devices, energy storage devices, and electrochromic devices. So about 7 labs of CSIR coordinated, or the mission directorate here at IMMT, and NIST Trivandrum, SICRI, CGCRI, NML, AMPRI Bhopal, and NAL, Bangalore. They're all working for this. There are many other initiatives we have started. I am disheartening to tell that we have started an incubation center called INTEC, Innovative Technology Enabling Center. We have 14 incubators already present. Even the COVID time, we come up with a building for incubation center. We have come up with a common research technology development hub, which is to help the MSMEs. This is a project we got from DSIR, CRTH, and this house here in the campus helps the MSMEs in the sectors of minerals and materials and chemicals, the local MSMEs, the artisans in Dokra or brass, bell metal, filigree. So we are helping them in many ways, whether it's a benchmarking, whether it's IP, whether it's improving the quality of the product, the finished product. We're also working on Moradabad cluster on this. So these are the new initiative on the Common Research Technology Development Hub and the Incubation Center, which is recognized by Startup Odisha as one of the incubation center. So just to tell something new that we are working on, along with non-ferrous metallurgy, extractive metallurgy. We were working for a long period of time in hydroelectrometallurgy department, and then low lean grade iron ore processing or reduction roasting. We were working for a long time in mineral processing department, and we are looking at a magnetite ore these days, how to process magnetite ore by using different techniques such as microwave or the mineral processing or concentration of magnetite ores. So many others apart from beach sand, monazite, and all those things I just talked about when I talked about neodymium. So with this, I would request all of you, and especially Professor BK Mishra, that we are going to celebrate 60th year next year, and I'm sure he will be here and will be helping us in many ways, as well as all the dignitaries who are present today. Whether they're joining from Bhubaneswar or Odisha or anywhere in India or the world, that IMMT will be celebrating 60th year existence next year. And I'm sure there will be huge participation from all of you and help us in many ways to be a program of great success. I now, of course, honored to introduce Professor BK Mishra, who is the director of IIT Goa at the present, joined in 2017. Prior to that, he was director of CSIR Institute of Minerals Technology. With that I introduced just now, he was then helm of it for 11 years, and he has done tremendous development work for IMMT Bhubaneswar. Prior to that, he was in IIT Kanpur as a professor in metallurgy department, and then he had visited visiting professor University Utah and many other places. He's fellow of Indian Academy of Engineering. He has guided 14 PhD thesis, and he is a very active man in the area of in the area of modeling, mathematical modeling in application to materials or mineral processing. So he has developed some of the commercial software like MillSoft, SeamCyclone, and SeamJig. So these are being implemented, these are being taken up by different industries, and quite a successful in terms of developing the code or developing the understanding. Once you do the mathematical modeling, you can really understand the whole process, which is not possible entirely through experimental technique, which could be a very regime of operation could be very small, whereas modeling, of course, can give you a whole regime of operations and understanding of the physical phenomena that is taking place of any of the mineral processing operations or unit operations. With this, I would request Professor B.K. Mishra to give lecture on discrete element analysis of particulate system. It's a very tough subject because DEM is quite popular once as a technique, and particularly in particulate system, when you do not have in a fluid system, you have Newtonian or non-Newtonian, whatever, maybe you have a continuum, and your continuum system is easy in that way. Even if you use Navier-Stokes equation, whether discrete particles or particulate system, one way of doing in a particulate system is to assume it as a Newtonian fluid or Newtonian flow. But whenever the holdup goes up, you have more particles, then of course it cannot be taken as a Newtonian fluid or as a continuum fluid and continuum. And there it's very, very difficult. And I know that this flow systems in the particulate is absolutely difficult to analyze, and results vary case to case, time to time, and equipment to equipment, and the flow system or the control volume that you have chosen. So with this, we are looking forward from Professor B.K. Mishra to enlighten us on this topic and give his deliberation. Thank you.
Let me share this. Is it visible there?
Yes.
Okay. So first of all, greetings of.
You maybe want to go to the projection mode, slide projection mode, full screen.
Yeah, I'm on full screen.
No, we are not full screen here.
Oh boy. Is it full screen now?
No.
Okay. Okay. This is a problem.
You might want to share your whole window rather than the PowerPoint.
I'm sharing. There are.
If you share the window in the whole window,
okay,
instead of PowerPoint, then it will work.
May I suggest that you put your computer on full screen? I have done it on full screen. Now I am getting full screen, but not your slides. Your slide is not coming, but you are coming full screen.
Oh, I see.
Share your window rather than a PowerPoint program.
Yeah, that would be better. I'm sharing my window now. Let's see.
Yeah. Okay.
Is it
Yeah.
Yes, now it has come.
Okay. Okay. So at the very outset, let me thank Professor Basu, Professor Acharya, and other distinguished members of INA, and Professor Mahapatra, of course, And today is Bahuda, and my greetings to all of you. At the same time, my professor is no more, Professor Somnath Mishra, who taught us, the fast course of material science. I took a couple of courses from him, and while in Bhubaneswar, I had several occasions to interact with him. Unfortunately, he passed away today, and fantastic professor. At the age of 30, he became a professor at IIT BHU, and then later on he moved to NIT Rourkela as our principal. Did his master's and PhD from MIT. Never stood second. So a brilliant person and a visionary indeed. Okay, so Professor Acharya, you recall when we had the INA meeting convention in SOA campus.
Yes, yes.
That time you thought of this coordinating this particular activity, but it never materialized. I'm so glad that now you are doing so many things locally, and so many people taking interest in this particular activities. And that also gives us an opportunity to share our thoughts and know more about other institutes. That was also not happening in Bhubaneswar. Anyway, as far as I'm concerned for this occasion, since I'm in Bhubaneswar, I'm talking to people in Bhubaneswar, where a lot of mineral processing activities do take place. I thought that I'll share some of my experience relating to modeling of particulate systems by using discrete element method. This was something I did way back in late 80s, and that time it was perhaps I was the one for the first time I introduced this to our community, and the code that I wrote as part of my PhD thesis was in fact circulated free of cost among our peers. So today, that was then, and today you see a lot of our computer software, including even Fluent, ANSYS, and all those softwares, and we have purchased the Siemens package. All of those software, they have discrete element analysis tools there. Now you can apply this to different systems, and I'll restrict myself only to systems containing particles and where particles interact and stuff like that. So as a prelude to that, when we talk about particulate materials, they are kind of strange. They're not liquid, neither gas nor solid. So they, unlike gases where elastic collision should take place, here in inelastic collisions, and liquid, if you pour a bucket full of water on the floor, then it's going to spread. It will not do. Particulate materials, they will stand there with the angle of repose, so on and so forth. So this is a new class of material, and physicists are particularly interested in handling some of the nuances of these materials. The underlying phenomena that we observe here, as in second system, arching in hoppers, mixing and segregation in rotating systems, avalanches in snow-covered areas. Then, of course, agglomeration. I'll touch on some of these aspects and simply show you the simulation. There are fundamental statistical as well as dynamical challenges. I know no two particles are alike. Therefore, we look at statistical methods to get some characteristic features. And in particularly in rotating system, particles evolve in a periodic manner, but sometimes they could behave in chaotic fashion. Well, the interest lies in the fact that the global aggregates market in 2019 was pegged at $463 billion. Mining industry, $656 billion in the same period. And put together, this is about 1,000. And compare that to steel industry, it's only 861 billion. Therefore, there are obvious reasons to analyze particulate systems. So I got caught into this and started looking at different aspects of particulate systems. So what I'm showing here is that these kind of size reduction.
Professor Mishra.
Yeah.
Because you are not in the slide mode, full screen mode, I think you are not in the first slide, right? You must have moved to.
Moved. Oh, I see. You are not seeing it.
No. Now we could see the third slide because
Yes.
not in the. Now
I don't know why it is happening like this. I did what you said to do. Share
it is not working. So now, this is now working. You can choose your slide from the sidebar, and then
yeah, that's okay. Okay, so that's sorry about that, and I can't do it. I looked at Windows mode and it's not working. I'm more used to Zoom, and here it is like this. I can't help it and waste your time here. So let's start with mechanical crushing. And why I do that? Because it's estimated about 4% of world's total power is consumed in size reduction alone. So tons of, on the top of that, tons of steel is also consumed as liner, lifters, and grinding media. So how much power these monster size machines they draw? I mean, it could range from 2 to 30 megawatts, depending on the size of the mill. So size reduction to produce metal, if you go to Tata Steel or some other, particularly in non-ferrous industries, it could go as high as 50% of the operating cost. Industrial facilities also operate below design capacity. Therefore, a lot of scope for consulting. And I, for one, did a lot of consulting for many industries. And the right side figure that I'm showing you here is one startup activities which I did in IIT Kanpur. Today, the company sells these machines. I'm no longer associated with that company anymore, but I did that. Now coming to the issue here, traditionally people, they were doing mechanical crushing, they were analyzing, designing, and everything was going on with what you call population balance modeling method. So this is a black box type of modeling method where it works only up to a certain size of mill. But when you talk about industrial milling systems, this whole thing fails. So during 80 to or mid 70s to late 80s, people, they were worried about this, and they were thinking of coming up with a newer technique. And that's the time when I started working on this problem. So we realized that the only alternative that time that was existing was a direct simulation method, which was discrete element method. I used successfully this method to look at particle breakage in industrial size grinding mills. So the concept is as follows: instead of solving those big equations, which are in certain cases insoluble. So in fact, I have solved some of those equations. They are one such equation, integral differential equation. Here I solved using Monte Carlo method. It's there in Chemical Engineering Particle Breakage Handbook. But very tedious, very tedious. So we wanted to look at some simpler methods. So what we did is that we said, if I know that how the energy that is the drive system supplies to the mill, and how that energy gets distributed across all the impacts that are taking place inside the mill, then perhaps I can calculate the particle size distribution, overall particle size distribution after the end of the simulation. So we had several drop ball test type of experiments. Here I'm showing that I'm dropping different balls from different heights onto bed of particles. And after those particles have broken, I look at what these particles are broken and what's the corresponding size distribution. This data allowed me to estimate and to calculate the overall size distribution particle breakage. Now, but the question is how to get this impact energy spectra, impact energy distribution in a very large size mill. Clearly, experiments will not allow you to do that. Inside this mill, very harsh environment, all sensors will break, will fail. Only recourse that time was a discrete element method, direct simulation method. So what is discrete element method? So as Professor Basu said, it's a method treating discontinua. And so prior to this, they were using finite element method, treating the material as a continuum. So from this point onwards, we started looking at it as a discontinua. And what we did is that instead of doing the whole particulate system, well, let's focus our attention on individual particles. So we allow particles to interact, and different types of particle interaction is assumed. Now, how they interact, that's quite, that will be again mathematical. I'll leave that to some of the papers already available in the literature. But at the end of it, what we do is that to track the motion of one individual particle, we apply Newton's law. That is, sum of forces acting on a particle equal to mass times acceleration. So here is the algorithm. So we go particle by particle. We identify which particles are in contact. For example, in this case, these yellow particles I and J, they are in contact. And we replace the contact with a set of engineering units like springs and dashboards. And then the further interaction will be controlled by the spring and dashboard behavior. And we are to make it realistic, we say that the total shear across any contact cannot exceed the coefficient of friction times the normal force existing. I'm not going to get into that, but this is the equation, the Newton's second law, that sum of all forces is mass times acceleration. So if you know the acceleration, you can integrate, find the velocity and then the displacement and the new position. So with time, if you keep doing that, then the whole en masse position from one time step to another time step will evolve. So having set the contact model in this manner, it is possible to calculate how much energy is expended by moving the en masse particulate system to one time step to another time step, and you sum over that and you know the energy expended in that. But in all this, the major challenge is finding the collision, which particle is in contact with. So there are different schemes available. Computer science people are very smart. I did different types of collision detection scheme. Even now I am doing that. So simple partitioning boxing scheme to other data structure like tree structure, tree structure, and assuming particles as polyhedrons, and looking at Voronoi polyhedra and all that, all these things one could do. Then you apply, once the contact detected, then apply Spring Dashpot and calculate the trajectory, update the contact list. So this is the whole scheme which operates under a time loop. Now, I'll not get into that, but the way it works that you take a bunch of particles and then have proper contact models. So you can have a simple elastic linear contact model. You can have non-linear elastic model, elastic plastic contact model, and you can, even if you want, you can have some strain hardening. For some systems, we have applied JKR theory. I'll show you some results where adhesion is included. And once you do all these contact models and everything all set, you will get the complete particle dynamics. And if you have agglomerates, you can analyze agglomerate breakage, the force transmission paths, and whatnot. I mean, like Professor Basu mentioned, the entire process regime that you are searching, it will unravel from this point onwards. So here is the charge motion. This was done for the first time in this manner. So these are million particles simulation done in high-speed computer, and later on we parallelize. And in parallelized computer system, one could do direct simulation of industrial size mills. So this I was doing a Kennecott-Copperton mill simulation. Now, why we do that? I'll just illustrate that by showing it to you that these mills, they operate carrying a lot of load inside, and if they slide or slip, then the mill will get damaged. Therefore, you can see these protrusions are there. So their configuration and arrangement is critical to the grinding or breakage process. So we do that by set those parameters by simulation. The industry norm, what is there, came out of our simulation, how to design these mills. And after mill shop, one of the manufacturers, Calcutta-based manufacturers, they are using my simulator to design their milling systems, and they are one OEM company there. So I know the size, I know the energy spectra because I'm simulating the charge motion. So here is the energy spectra. So once the mill rotates, are you able to see that?
Yes, sir.
Yeah.
Yes,
So,
yes, we can see that.
Once this rotates, right hand side, I draw the energy spectra, and with my method for each energy impact, I know the size distribution, what it will come. So I calculate the, not in real time, but as soon as you give me the energy spectra, I'll give you the size distribution. This was very successfully implemented in different plants across our country. Kudremukh is one, Kiriburu is another one. Kudremukh I did when I was at IIT Kanpur. I was doing this, and Kiriburu, of course, I did it also from Kanpur. Now, in Bhubaneswar, we looked at, hey, particles are not just particles, they have valuable material, they also have waste material, and they are joined together. Now, if you break these particles, make them smaller and smaller, now the question is, okay, size is reducing, but what happened to the valuable portion? How that gets distributed? So here, what we look at is that this is again another complex problem depending on the grain structure. Here I am showing white material are the waste material, black ones are the valuable material. Now I come up with a methodology to find out that if I fracture these grains, then what fraction of the material in the entire broken particle population will be of certain size as well as of certain grade. The equation that you see bottom below is really not possible to solve. There are geometric methods available, but those are quite complex. What we did in Bhubaneswar, say for example, in those days at Bhubaneswar, we were looking at banded hematite. All these companies, Tata Steel, if you go to JSL, they were all good ores were gone and they were getting this sort of banded ores. Now, the question is how much grinding you do to get your valuable material out. If you do over grinding, there is loss of money. And if you do under grinding, that's also loss of money because you are not going to recover all the materials out. So here what we did, how do I show it? Okay. Let me see if I can. So we took a geometric modeling approach. So we had a banded rock there, if you can see. Onto that, I impose a crusher and it's going to break that banded rock according to the crusher geometry. So the crusher that you see, the mesh, those are small, small cubes. So if this crusher is imposed on this, then it will break. So this is only binary banded. You can make it even more complex. It's computer doing. I'm not doing any experiment here. So this is what I was doing in Bhubaneswar. So these are black and white kind of rocky banded particles, and we break them. Now in the computer memory, we go and look at how many broken of the entire population, how many are white, how many are 100% black, and how many are those mixed ones. So that's easy to calculate, and that is what the spectrum will look like. So this was a major breakthrough in our analysis, and we published this, and this was again done for the first time. So so far I have discussed with particle breakage and then the distribution of grade valuable material, how it gets liberated, so to speak. Now I'll take you to another topic where you can apply GEM to look at breakage of agglomerate. So you can think of these as dust agglomerates. So these are very small dust particles. Dust, nothing but those are again collection of very small particles, and by virtue of van der Waals forces, they get attracted and form a dust particle. So this is something, if you want to study how these dust particles break and eventually spread, it's very difficult to do any experiment because in your instrument machine, you cannot hold a dust particle of this size, 100 micron, let's say, or even 1 millimeter. You can't hold it. So in the computer, we generate a particle assembly, and this work is still going on here, meaning the packing aspect for some other application I'm doing. So I'm showing you what I'm doing. Basically, I prepare one agglomerate, and in the agglomerate, I put some glue into it. Glue spreads inside the agglomerate here and binds it. It's just like laddus that you get in sweet stalls. So once these are made, then you can prepare these agglomerates in different way. Left is a random agglomerate. You can make it also regular agglomerate with proper packing as per a stacking sequence. So here I'm looking at how agglomerates break. In this particular numerical experiment, these daughter fragments forming the agglomerates, they are packed in a regular manner according to hexagonal closed packing. So when you have regular crystalline agglomerates and you drop them onto a plate, like I'm showing here, drop it, then those agglomerates, they break in a faceted manner. Okay, and as you can see, there are facets and they are breaking in this manner. However, if you move to random agglomerates, which is the case, which is the real situation, and if you want to look at their breakage behavior, they, as you can see here, they will peel off like oranges. So this was also, supported by Dow Chemicals, and this was one work we were doing to study clean room behavior, and so this is how you will do. After studying so many agglomerates, we realized that these agglomerates will eventually break in 4 breakage modes, which is called fracture, shatter, disintegration, and total disintegration. And they are depicted here. Now, we also looked at how the fabric, supposing you have one agglomerate around a strong fabric, then if you drop it onto a plate, it depends on the orientation of the fabric with respect to the plate. As you can see here, if in the Y direction you are dropping it, and in the X direction you are dropping it, and the Z direction, the eventual behavior of the agglomerate going to be quite different. Anyway, this was studied with a different purpose. I'll not get into that, but one could do this sort of analysis. What is the application as far as our minerals and particles concerned? Agglomeration is routinely done in our industries because you have to grind these materials finer. Once finer, you can't put them in blast furnace, they will fly off. So you prepare balls, or this is called a balling process or agglomeration process. This was for the first time simulated here, and we show the size distribution. Initially, it was blue line is a finer size agglomerates. Red line is a coarser size agglomerate, and we studied this thing in detail to unravel the mechanisms of granule formation, growth, and breakage. Now, one last topic I'll also did something out of curiosity. Powder mixing is also a very interesting area. When mixing, you talk about mixing, alongside, of course, there is segregation. So these granular materials, they segregate in very interesting fashion. That will be another topic some other time. But let's focus on powder mixing. In many systems, chemical engineering people, they know it better. In many places, you require mixing. You go to pharmaceutical industries, you go to food industries, in many places, it requires mixing. But mixing is easier said than done, because simple black and white type of particles, if you try to mix, it will never mix. So you have to design these mixers in a proper way. People, they have, L-shaped mixtures, cylindrical, yet funny shaped mixer, and they try to do that, and they rotate also in different ways. So the complex nature of particle interaction has defined really a good understanding of particle mixing, and it's been going on, and even today as I speak, people, they are working on it. So this was at Kanpur. So as part of one of our projects, we were pouring white and black particles into two compartments into a cylindrical vessel here. Okay. And then we rotate it slowly. When we rotate it slowly from this side, from the side where we poured our material, this is plexiglass. From the side where we poured our material, after mixing is over, we see a Doordarshan logo. And this is what was going on. Oh, the backside was a black tin plate was there. So we removed that. We put a plexiglass also there and looked at that side. When we looked at that side, we realized that at the center, the material is same as before, as we put it there. No matter what we do, this core never mixes. Whereas from the other side, it is a logo, Doordarshan logo that we said. We did a detailed analysis this, and I came that time to Bhubaneswar, and we did it. Are you able to see this?
Yes, sir.
Okay. So this is what you do, that the mixing index, meaning the extent to which it mixes. Now you are able to simulate and also quantify, to what extent these particles mix. If they are not mixing, which I'm not putting here, we designed the whole system with incorporation of baffles, and that allowed complete mixing. At least the mixing index was found to be much better there. So finally, I am going to conclude it here that this tool has emerged as a very practical method to study in particular industrial milling systems and associated breakage of particles. Now breakage, I dealt with it indirectly, not by direct means, but what I'm currently doing, that instead of a geometric modeling approach, that each of these mesh I'm right now connecting with springs, so that we'll get a more realistic breakage pattern if we are going to study this in more detail. Mill diagnostic is another area which we developed imaging tools in Bhubaneswar, and also vibrational analysis we did for some plants there. And that is also possible by using a software, and this is becoming a diagnostic tool, just to know that when the liners will be changed and when the liners will be replaced. If they're not replaced on time, then the steel ball is going to damage the mill. We applied this in several plants in India. So in addition to that, advances in DEM has reached to predict direct breakage of particles, but there are issues because it's nobody's guess. It's once a particle breaks, how do I know that how many daughter fragments will be created? If the impact is too much, then one particle could lead to million particles. And for that, to track those particles, you need proper computing power and storage of data. So those are the limitations. Other than that, simulation of dynamics of powder particles in a variety of situations handled. And I myself, I have done fluid particle, which I didn't talk here, fluid and particle interactions are applicable to jigging system and hydrocyclones, for example, that software Professor Basu talked about, that came from another company also in Calcutta, and we supplied that software to them. So anyway, thank you very much for being so patient. I mean, no, this can't be a general talk, but I thought this is the best I could do to make it as general as I could. So thank you.
Thank you very much, Professor Misra. Now, Professor Sharma, would you like to handle the Q&A?
Yes, sir. Yes, sir. So I would like to invite Professor A. Sanat Kumar, sir. Sir has raised the hand.
Can you hear me, please?
Yes,
Am
sir.
I audible? Okay. I have 3 sub questions essentially. I'm not very sure whether they are relevant or not. So please bear with me. Number 1 is, you have assumed the particles to be spherical.
Yes.
Given some time, it's not necessary that all particles are spherical. Second is, the particles may not have the same hardness. So you are saying you are using springs and something. I am not very sure how the difference in mechanical properties of the particles are covered. And the third is, particles may not be of the same size. One particle may be bigger than the other particle. If a particle has got sharp corners, it may break in a different way. If the particle is smaller, it may escape between 2 particles. I don't know. I'm just imagining. So how do you deal with this?
So very good question. And the commercial software, they have these features that you can have particles of different shape. There was a time I was also working with to the extent possible with elliptical particles. But even for simple ellipse, if you solve the equations simultaneously, these are 4th order equations, and the roots that after you solve, you get into real and complex realm. So these are quite difficult, and people, they have been doing it. The alternate route is that you write the equation of a cube, ignoring the sharp corners, by what are called superquadrics. So, and then those equations you can solve simultaneously and do that. As far as I am concerned, I haven't dealt anything beyond spheres. Once I did for ellipse because of some other reason. Now, second question is hardness. Hardness comes, I haven't dealt with that so much, other than specifying the strength at the contact. If we use Hurgian contact theory, then the you can put shear strength and other strengths into account. That if one could consider as hardness, then that would be the case. And different size, yes, size is something we can use it at our will. That's not an issue. Yeah.
Okay, thank you.
Any other questions from the esteemed participants?
I would really like to raise one small thing. Once I went to one of the factories of Hindustan Lever in Daman,
Yeah.
and they do produce there some powder materials, and more specifically talcum powder, which actually we use. So then one thing they told, which may be correct, I'm not very sure, that a talcum powder quality depends on the uniformity of the size of the particle.
Yes.
And a good quality talcum powder will have more or less same particle size when you powder it. The similar thing I understand when you mix also different compounds for manufacturing of medicine, you require also similar size particles. And through this grinding process, how do you really ensure that the particle size are same?
No, as I said, no two particles are alike, no matter what you do. But we classify them and say that within a certain range, they are alike. So it's like that. Preparing very fine powder of same size has been a challenge. And it was even in those days, if you recall, magnetic tapes, audio tapes, video tapes, there
Yes.
we used to coat magnetite. And if the size and shape is not proper, the audio glitch noise will come. So these have been a challenge, but the mill, that startup activity that I showed you, that it is a high energy dual drive planetary mill which we are supplying in India. Sir, what these machines, they only operate without impact. They what you call gauge or cascade through inside the mill and rub it off from the surface slowly and steadily. And beyond a certain size limit, you cannot mechanically do anything. So that's your limiting size, and that's your talcum powder.
Yes, yes. Okay, I understand. Thank you.
Or you can go into chemical methods. Yes, you can do that. There you can exercise control. But in mechanical processes, it's a challenge. Yeah.
Okay.
Yes.
What do you do in a ball mill? In a
Yeah,
ball
it's-
mill, what happens?
Yeah, these are ball mill applications. It started with ball mill, but in case of a ball mill, the impacts are random, and they don't select particles in that manner to break. Whatever particles come in the collision zone, those are the particles that's going to break. Some really escape without breakage, some break. So we model that process and try to see that how we can design the mill by those. I showed the lifters that how to control the speed and level of filling to attain a certain particle size distribution. Grinding mills are used not only to reduce the size but also to liberate particle. Let's say copper, I'm doing it. If copper particle is not liberated, then you end up with a lot of quartz or something like that. So it's a dual. So you have to look at it very carefully. So
Thank you.
But I'm not finding anybody's hand raised, so I think
Now may I request you actually to propose a vote of thanks, summarize and propose a vote of thanks.
thank you so much, sir. It's my proud privilege to extend the vote of thanks to Professor here at this juncture. Professor has wonderfully explained about the complex nature of particle mixture, and he has narrated beautifully with various live examples what he has experimented in various mills. On the onset of this, I would like to extend my once again heartfelt thanks to Professor P.K. Mishra sir for giving us the valuable time and valuable lecture at this juncture. Thank you so much, sir, for joining us and giving us your valuable time. Thank you so much.
Thank you. Thank you very much.
Okay,
Thanks,
thank you
thanks.
so much.
Thanks, Professor Acharya.
Thank you, thank you.
Yeah, thanks.
I wish you a very, very happy Bahuda.
Thank you. Thank you.
Thank you.